Hello everyone and welcome to this webinar. My name is Michael Evangelista and I will be your moderator for today. Just a few reminders that you are in listen only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want and those questions will be answered by our panelists in a Q&A segment. The recording and certificate will be set out in 2 days time and our topic for today is a guide to battery bank condition assessment. This is a pre-recorded webinar and it was presented by our experts from the US. So without any further ado, let's start the webinar now, Grace.
Hello everyone and welcome to today's webinar on a guide to battery bank condition assessment. My name is Sanjay Yadav and I'll be hosting this session today. Speaker for today's session is Mr. Ali Hussain, who is an application engineer at Megger Middle East. Before handing the mic over to Mr. Ali, I would like to highlight a few points. You all are muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session by Mr. Ali. I would like to let you know that we have come up with Megger Middle East exclusive page on Facebook and LinkedIn. So I'm sharing the link in the chat window. You can go through the link after the webinar and you can just follow us for regular updates. Also, we have a lot of upcoming webinars in October, which will be very suitable to you, which you can go through that link and register yourself. This webinar are free of cost, so you can just register and attend the webinar. So now I hand over the control to Mr. Ali. So let's get started. Over to you, Ali.
Thank you, Sanjay, for the introduction. Welcome, everybody. Good afternoon or good morning for you, wherever you are. We have an enough number of participants already with us today, so I will go ahead and start directly. Our agenda for today is very light. We will first talk about battery types and battery applications, where they can we use them, and some important information about them. Then we're going to talk about failure modes in batteries and why they happen and how we can overcome them and what this failure mode means to us in testing. After that, we will talk about some testing methods that we can do for battery maintenance, specifically talking about ohmic testing. We'll talk in details a little bit about it and some of the pitfalls and maybe issues that you might face that we can overcome and handle much easier. At last, I will give some maintenance scheduling as an example for you, a reference to help you in planning your maintenance for battery banks and systems. So without further ado, let's start with battery types. So in basic, battery types come in two way, primary cells and secondary cells. Primary cells, these are the non-rechargeable batteries that we use in our everyday life. And from the name primary, that means once they are manufactured, they are ready to use, we use them, utilize all the charge in them, and then we throw them away. Secondary cells, however, they are rechargeable once they are manufactured. We recharge them to be able to utilize them, and once we discharge them fully, we can recharge them again and use them for a long period of time. Our presentation and webinar today will be mainly focusing on the secondary cells, since these are the one we utilize over a long period of time. I will talk about their types, applications, failure modes that we see in them, and then extensively on their testing. So starting with secondary type cells, They mainly include a lot of types, but we mainly focus on 3 types since they are the majority available in the market. The lead acid family, we talk about the types that have some of the problems and failures happening in them. The nickel cadmium batteries, since they are available extensively as well. And nowadays, since they are very popular, the lithium ion battery, we'll talk briefly about them since they are a big and huge family to cover in this webinar. Starting with the lead acid cells, basically you can divide them into 2 sector: cyclic batteries, where you are using them on a regular basis. These are mainly common in automotive batteries or portable battery operated devices. They are usually or regularly charged and discharged and used frequently. The another segment or type is standby batteries. These are where we find them in a standby mode. They are not used unless they are needed. And usually they are very famous in substations, telecommunication, and data centers for the UPS systems. So for the battery types, even further in lead acid, in terms of chemistry, there are a lot of types and several different types of chemistry. However, we have 2 types of chemistry that will usually found is the flooded cell, ventilated lead acid, or the sealed one, ventilated, regulated, valve regulated lead acid cells. There are some differences in the way they operate, starting with the flood cells, the ventilated lead acids. They vent hydrogen as they discharge, and some people might consider this dangerous things, but usually once they apply this battery, will usually have a ventilated place for them to contain them as one of their requirements. The very good thing about these type of batteries, they can last for a very long time. And if they fail in what we call the short mode, means that the current can pass through them through a string. So if you have a critical load type, this battery, you can rely them even if one of the cells has failed and a string, you still have that string operational for you. The only con for them is that they vent hydrogen, and this does lead to exhausting the water content in this electrolyte of these batteries. Thus, they require to be added distilled water to them periodically, and thus their maintenance is quite extensive. But they last a long life. In order to overcome this issue, they have the different type, the sealed type, or some may refer to maintenance-free batteries, valve-regulated lead acid batteries, which have a recombination of the hydrogen. They still vent hydrogen, but they recombine it inside the cell itself. So they recreate that water content inside the battery. Of course, this is not 100% efficient procedure. So they do fail quietly. They have quietly shorter or relatively shorter lifespan compared to the VLA batteries, and they require temperature controlled environment, since this process of failure can be accelerated fastly in high temperature environment, and we will talk about this type of failure in the failure mode sections. Next, we have the nickel cadmium batteries. They have different chemistry than the lead acid battery, which give them a better, you can say, a better capacity to weight or size ratio. So they really can be used in a small environment better than the lead acid batteries. They have relatively a good lifespan from 10 to 20 years. compared to the valve regulated batteries. But if they fail suddenly. You cannot really easily detect or trend their failure rate easily. That's why you see the lifespan from 10 to 20 years being a huge gap in it. Next we have is the lithium ion batteries, and lithium ion batteries is not really easily can be classified in this presentation. They are huge and big family of batteries using different chemistries and characteristic. And their characteristic and chemistries really depend on the different applications. Some different application will have a trade-off. This is a table showing you some types and different chemistry of lithium ion batteries, and some of the trade-off that they can give you from safety, power, energy, and cost, and also lifespan of each type. So it's really depends on the application. You will have different type of lithium ion battery. So with that said, we will go through now some of the application of the battery usage and how it affects its maintenance period as well. For battery application, you have to keep in mind that batteries are not created equally. Different application require different design. And the battery basically have two blades and electrolyte in between these blades. Now, this blade design will and surface will be different depending on the specific application. We'll talk about that briefly. So starting with these blades, the blades created more thicker or bigger for application that have regular heat generated, usually charging and discharging cycles. Mean for a cyclic uses application, these blades are usually made thicker to be able to handle or transfer the heat more efficiently, thus lasting a longer time in charging and discharging cycles. And they could be created even thinner layers of the blades if they have different application, like requiring a huge current supplies for starting application or for a temporary short period of time. For lead acid batteries, they basically have two different chemistries inside. You have lead antimony and lead calcium. The lead antimony chemistry for that, it is more tolerable to heat generated from repeated cycle and charge and discharge cycle, but they are not very good, or cons of it is not that very good in standby application, because the lead antimony has a poisoning phenomena that could decrease the capacity of the battery if it's not used regularly in standby application. On the other hand, the lead calcium batteries deal very well with a float application, meaning a standby application, and does not deal very good with repeated charge and discharge cycles. So they are very much better in standby application. From that, we go to the cyclic batteries. These are the batteries that we use on the regular battery basis. From the previous slide, we know that these are better designed in the lead acid family to be lead antimony design. They have usually a stronger or thicker blades to be able to accommodate the heat generated from charging and discharging cycles. And they are not very good in floating or standby application, as because of the antimony poisoning. So it's really better to always keeping constantly usage in cyclic application to have a better longevity in these lives. Stationary batteries or application, this is what we usually will focus on in maintenance and in planning and testing. These are used in substation, telecommunication, and data centers. Usually they are lead acid design. They are very good for long period of floating because of no antimony poisoning, but using them in heavy cycling, like charging and discharge cycling, will reduce their life cycle pretty drastically. Another application that is in between these two is the SLI type of battery. They call starting, lighting, and ignition battery types. Usually we use them in cars. These batteries are designed not to be charged and discharged rapidly for a deep discharge, but to be able to supply a huge amount of current, or huge amplitude of current for a small period of time to be able to start these cars. And also they are not designed to be deeply discharged, as it can really minimize their life cycle pretty drastically. And one note here is that if you have, for example, your battery died in your car, for example, it's better to jumper it and then replace it further, or in shorter period of time, rather than just keeping it for a longer time, because once this battery got discharged, it will lose its life pretty drastically, since they are not designed for this application. Then we have the nickel cadmium batteries. As I mentioned earlier, they have a good capacity to space ratios. They are very good at limited space, and they have a very good deep discharge cycle. So you can discharge them pretty much to very low range voltage, and they will still be good in good condition, and they can be tolerating a huge wide range of temperature. That being said, even temperature does affect them, even with this huge or wide range for temperature. Still, it will be affected, but the effect will be less than lead acid batteries. Last but not least, we have the lithium-ion batteries. These batteries, you will usually find them in packs consisting of a smaller cells in series and parallel configuration to accommodate any voltage and capacity requirement. As you can see here from the picture on the top, you have cylindrical type of cells, and you can see attached to them an electronic chip. As this type of lithium-ion battery, voltage balancing between the cells and charging and discharging cycle is very critical to their life cycle. And also, usually you will find with these battery cells or battery packs, battery management system to manage their charging and discharging cycle efficiently and equally between all the cell. And this battery types, or lithium-ion battery types, really have a huge applications for them, but you have to choose a select chemistry for that application. This was some introduction about some of the batteries and their types and their applications. We will go now to failure modes. Some of these failure modes that I'm going to show you relate only to some type, and other failure modes relate to another type. So please keep in mind that for this segment. So the first failure mode, called positive grid corrosion, and usually a normal failure mode in lead acid batteries. And when I say normal failure mode, it's an aging mode, or aging failure. So with time, this will be happening in your battery. It's a normal corrosion happening. It will happen no matter what you do. But the very important thing here is that we do not accelerate these chemistry changes by doing an overcharging to our battery, or excessive cycling, charging, discharging excessively. And we make sure that they are maintained in a good temperature, not to accelerate that. As you know, chemical reaction happen faster in heated environment. Even 10 degrees increase could increase the reaction rate by double from basic chemistry knowledge. The good thing about this type of failure is that it's easily detected by doing an internal impedance for each cell. You can turn this to detect that you have corrosion inside your cell. One thing to note is that the plates, as you can see from the picture, will grow once this corrosion happen, and thus they leave spaces. You can see it in below, some space available for when this corrosion happen and the plate grows, the cell can accommodate this growth since it's a normal procedure. Another type of failure mode in lead acid batteries is self-heating. Now, this failure mode happen in normal charging and discharging or discharging cycle. It will happen normally a neutral process during the discharge. Now, the discharge, once you discharge this battery and the self-heating happen, once you recharge the battery, this process will be reversed. So it happens and could be reversed in one charge discharge cycle. But the very important thing is that if you don't charge fully, some self-heating crystals could form, and if kept under charge for some period of time, this crystal can harden over time and result in a permanent loss of capacity. The good thing, if this happens, you can detect it by increase in internal impedance. And there is a mode of operating or charging the battery called boosting mode. If you put your battery in or charger in a boosting mode, it's designed to eliminate these sulfate crystals from your lead acid batteries and really reverse, you can say, the undercharging cause of these sulfate crystals. But if you put them to harden over a very long time, even that boosting operation will not be helpful to you to eliminate this sulfate crystallization on your plates. Another failure modes that could happen is short inside lead acid batteries, and they come in two types: hard shorts and soft shorts. The hard short is usually once happening in the manufacturer, once the plates shorted with each other, and the battery, you will see it not functioning correctly and can be detected very easily from the beginning of the life cycle of this battery. The soft shorts, on the other hand, are caused by deep discharges. As I mentioned earlier, some of the lead acid batteries does not like to be deeply discharged. Usually about 80% of the cell levels will be like the zero charge for it. If you go below that, you will start to getting some soft shorts, and which in long time could result in a lower specific gravity, which we'll talk about later on, and could lower the capacity of your battery. The thing about this failure mode is that to be detected, it will create an impedance or will show the impedance of the internal impedance of the cell going down, so we can detect it easily with an impedance test of the battery. For valve regulated batteries, there is, as I mentioned, not a very long lifespan like the normal or the flooded lead acid batteries. The reason for that is a process called drying out or loss of compression. It's basically in the valve regulated, the water loss or hydrogen vented will be recombined to create water again in the battery, thus does not need water to be added periodically to this battery. But this process is not 100% efficient. So basically, in the end, the battery will be drying out of water. That's why I call it dry out. And it's a normal process happening, or a natural process to the battery will happen over time. You can detect it by seeing that the cell has expanded in size, and you can see it on the right side of the picture shown here. the important thing is that we do not accelerate this drying out by heat. That's why temperature control environment for VRLA batteries is very, very important, not to accelerate this process in the cells. And if this dry out happen even further, it could create thermal runaway in these VRLA batteries, which will draw more float current if you are using them for standby application, and create more heat. And more heat created will even further accelerate the dry out process, and you get on more heat will be created, and again the further this process until to reach a point where the cell explode or catch fire. Another failure mode here is the negative plate depolarization. It happened basically to the negative plate of the VRLA batteries. When they are not fully charged, this plate can depolarize, and thus leading you to a loss or excessive heat, which will also increase the dry out process in these VRLA batteries. The good thing about this negative plate depolarization is that it will increase the impedance or internal impedance of the battery, so we can detect it with doing AC test to these batteries, as DC test will not be able to detect these depolarization in these types of batteries. For nickel cadmium batteries, going to this type of batteries, we have a process of called carbonization or carbonation. It happens as an aging process to nickel cadmium batteries. Basically, the CO2 and the atmosphere get inside the electrolyte of these batteries and change the chemistry, thus creating a lower capacity in your battery. The good thing about this process that once you change or exchange the electrolyte of the nickel cadmium battery, you can remove this effect again, increasing the capacity of your battery again to its full or almost full charge. Another failure mode for this battery is called dendrite formation. It's as you can see, the picture here is taken by NASA. The nickel cadmium batteries create a dendrite formation basically in their separator and the electrolyte, and thus creating some short circuit between the two plates of the battery. This can be easily detected by the impedance and the voltage drop once we test this battery. If this short circuit has come to a very extensive level, it can result in a permanent damage or even battery burns. Moving forward to lithium ion batteries, they have what's so-called an aging process called SEI, layer building up. The SEI, it stands for solid electrolyte interface for this battery, basically decreasing the capacity of this battery by this. And this layer is formed periodically or naturally once the battery age, and it gets thicker with time. Each time it gets thicker, it blocks the blades from having a higher surface area, and thus really decreasing the capacity of the battery. As you can see, we're doing impedance testing for this types of battery. We can detect the increase or decrease in capacity. As you can see, in the y-axis, the capacity is decreasing when increased in impedance, and this some doing a lot of impedance testing over a long period of time can give you this, you can see an interpolated line indicating that impedance test is very beneficial to detect this type of SEI formation on the blades. This formation is done by maybe charging too quickly to the blades. When these charge and using a maximum rate of charging at different temperatures could really accelerate this reaction. That's why it's very, very important for lithium-ion batteries to have a battery management system to give a different charging rate at different temperature. As in different temperature, they will not accept some or constant charging type used by a normal charger. A battery management system is thus very, very important to prevent this type of failure. And last, we have another failure mode about loose connection. It's not related to the cells itself or the battery type, but to the connection. As I mentioned again, heat is really one of the big factors that can reduce the life of batteries. And having a bad connection or a loose connection can really generate a voltage drop on this connection, thus generating heat or waste of energy in this connection. And thus really heat is not very important. A lot of people don't really focus too much on this. It's very easy to do a resistance measurement on these straps, and we will talk about this in the test methods and the pitfalls happening for this straps measurement. And basically, actually, sometimes you can detect the failure or a loose connection by seeing some corrosion forming on the cell connection or the strap connection between the cells, as the picture shown here. Going to battery testing methods, you have to keep in mind that not a single test can give you the whole story. It's better to do a lot of type of tests to get a better picture. There are a lot of type of tests that mentioned here. Some of them are applicable only to certain type of batteries, and some of them is applicable for all type of battery. Starting with visual inspection, it's very easy just to inspect, checking that, especially for ventilated lead acid batteries, checking the electrolyte level always to the nominal value, checking the battery is not having any corrosion, cracks, leaks, thus indicating any failure, any deformation. For example, in the seal type batteries, you can find some expanding in their cells, thus indicating some drying out process happening. So verifying that there is no ground faults or leakage currents, and having a good ventilation and room cleaning is very important for the flooded type lead acid batteries. And one more thing I want to really mention in this is that the visual inspection, it's really good if you record this information regularly, not just checking by eye. Then we have the float voltage. This is usually done for standby application, where the battery system or battery bank is in a floating mode, means it's fully charged and ready to be used. Usually the charging have a floating voltage. It's very important if you are testing this floating voltage when you are using digital multimeters to use not to use a digital multimeters to do this type of test, because digital multimeter can give you false reading since they have a high impedance input to them for the voltage measurement. It's better to use a specified tester to test this float voltage, since this tester will draw some current from the cells, giving you a better reading that you can rely on. One more thing is that once you see a low float voltage, means they are not fully charged or having a plate Sulfation. If you have high float voltage, means you have either overcharging or and also overheating these batteries. Third test we can do is float current to measure the float current going through this battery in float mode. You can measure it anywhere in a string. And this float current usually will be very, very low in the float mode. If this, for whatever reason, the float current start to increase, this might indicate for you that either your battery is not fully charged, some of the cells are not fully charged. You can do what's so called float voltage to even confirm that even more, or you are having a ground fault in your string that can be detected also by a high float current. Rebel current, the float current was a DC test that you do to your battery charger or to the battery bank. The rebel current test is an AC current measurement. This is usually why do you have rebel currents. It's due because of charging system not being very efficient in smoothing out the output of these chargers. And by a thumb of rule from IEEE, recommended 5 ampere or a value not exceeding 5 ampere for every 100 ampere hour. Another thing very important in this AC current is the frequency of these rebel currents. If you have a very low frequency current, could result in higher float voltage. So when you do a float voltage test and then you do a rebel current measurement, and you see you have a lower frequencies of currents than or rebel currents, mean this could result in the high floating voltage measurement. And high frequencies usually are the batteries are susceptible to these high frequencies. They don't really affect them too much, but in case you have a lithium ion batteries which have a battery management system with them, these high frequencies could lead to failure or damages to your battery management system. So in case you have that, it's really important to check your charger or check that you don't have a high frequency content of rebel current. Fourth test we can do is the specific gravity test. What it's actually doing is checking the state of charge in the battery, not the capacity of the battery. The test itself is checking the ratio of the liquid respect to the density of water, and it's really highly dependent on the temperature. So you have to get your temperature correction correctly. There is a table for that. Now, so this test is, if you have a nickel cadmium batteries, this test does not really tell you anything about that. If you have a lead calcium batteries, that not really tell you the condition or state of health of these batteries. But if you have a flooded cells that have a lead antimony chemistry into it, this test can really give you if you have an antimony poisoning inside your cell, as it can measure that and show that very clearly. If you are doing floating current test, this measurement will be much more of redundant and not require that much. A fifth test or a condition that we need to consider when we are doing testing is temperature. I don't have to emphasize too much on this, as I mentioned again. High temperature will shorten the life, will accelerate the aging processes like the dry out for sealed batteries, and also lower temperature for some type of battery could lower the capacity, especially for lithium ion batteries. Lower temperature is not good as well. That's why they have the battery management system, not to charge the batteries at a high rate at lower temperature. As I mentioned earlier, a 10 degrees Celsius rise in the environment or temperature of the cell could result in a long time to having half the expected lifespan of the battery. Another very important and very absolute test is the discharge test. This is a test where you discharge the battery. It's the only absolute test that can give you the actual capacity of your battery or cell capacity. This test is not recommended to done in very short periods or very regularly. It needs to be done over years or basically done every quarter of the battery lifespan. Another recommendation with this test, as I would recommend once you get your battery delivered, to do this test to give you a baseline and to know what is the actual capacity of your battery actually by measurement, not by a specification sheet. But however, since I mentioned that the cells can fail between discharge test, another test is also recommended, and not only this one, since it's the most expensive test actually. One more thing with this test is that you can add a battery voltage monitoring system to it, or called PVM for short, which can measure the voltage during the discharge period periodically of each and every individual cell. That system comes with a lot of parts depending on how much cells configuration that you have. You can add that to detect any premature voltage lowered in any of the cells during the discharge process, and automatically even change the discharge or stop that discharge process, indicating that you have found a failure in one of the cells. We have the Torkel 900. It's a very good device to do this test. I urge you to check it out in the data sheets in our website. Another test we have is the ohmic testing, where we basically measure the impedance, resistance, or conductance of the internal cell. And as I mentioned earlier, the battery age, when the battery age, the chemistry change in the battery, and ohmic testing can see that for you. Ohmic testing is either gonna inject current through the battery and then look at the voltage drop on the battery. So it's really a very beneficial test, and there are some points I'm going to talk a lot about them later on. For the inter cell resistance, the straps between the cells, it is, if the torque is not sufficient enough, a lot of problem can be used, like higher resistance. We always want to do this measurement on the posts, not on the straps themselves, to get the strap measurement. Also, the connection between the battery and the strap could be checked with this posts measurement. And then to also mention about the battery terminals, it's very important, as I mentioned earlier, to check the connection between the terminal of the battery, the post, and the strap itself. And you do this usually by injecting a high current. For the ohmic testing, I'm going to talk a little bit in details now. There are three types: resistance, conductance, and impedance testing for the ohmic testing of the battery cells. The resistance test is basically is not wanted. Why this test is not wanted is because if you slip the reading and you want to take this reading again, you will have to wait for the battery to recharge again, because what this test does is that it pulls DC current, means it discharges the cell to the measurement. So it's not very repeatable easily in a very short period of time. You need to have the battery in the same condition each time you want to do this test. Another thing is another con is that the battery is not just a resistor. As discussed earlier, it does have a capacitive double layer on it, and this type of test will not be able to measure this capacitive properties on the battery. The other test, the conductance test, it's basically taking the reciprocal of the impedance, doing an impedance test and taking the reciprocal of this impedance. So basically, it's taking the impedance and dividing it into one. The cons of this test is that it's done in very low current. And you can see here the green wave, square wave, modulated square wave, that the test current used on the battery will gonna have a limited resolution. So you can get limited resolution you can get out of it, and it's not very good at larger cell, typically designed for VRLA cells since they are smaller in size. And typically this test is done at high frequency, usually 1 kilohertz. So if any noise is available, the test will be affected by this noise, especially if you have a UBS systems near the testing measurement done. This UBS system, you might need to shut it off to get a better measurement reading, or not to have the noise affect your measurement. Impedance testing, which is used for using a 4 lead Kelvin clamp. 2 leads will be pushing current, and 2 leads will be measuring the AC voltage. Then the impedance is calculated. The pros are that it is much more susceptible to noise, since we are using a high current for this test, and we do not need any algorithms to do this test because of the high current. As the cons for this test, it really depends on the testers. Some of them are not as high enough, can give you low current, and some of them give you high current for this test. So it's really important to see how large is the cell you are testing versus how much current you're going to use to do this test. Also, they operate at various frequency. Again, if you have one that operate at 1 kilohertz, again, you need to maybe check your UBS system or turn off your UBS system so you don't have any problems with noise. Very important thing about ohmic testing is that it's not an absolute test like the discharge test, where it will give you an absolute value of your capacity in your battery bank. It is much more a relative test. So it's not going to directly give you this cell is good or bad. This is, but what it will give you, or what it will show you, is that how much this cell or this battery have changed from the previous measurements. So trending and having a baseline and average is very, very important when you are doing this test, to see how much aged. And as I mentioned earlier, as battery age, the chemistry inside them do change, and thus the internal impedance of these batteries can be detected for different failure modes. Some tips when you are performing this test: always use the same model and same make between this measurement and previous measurements, to make sure that you are not using also a different test frequency or different test current, so you can really compare with your baseline value. And one more thing is that always make sure that you take the measurement from the same point at the battery. Usually we are using the post to do the measurement. If you are doing it from different points, it could change the result, and you have to compare relatively to these changes as well. Some of the pitfalls that you might fall in when you are doing testing. The first one is batteries have a low impedance. So the bigger the battery, the bigger the plates inside these, and thus leading to a lower impedance in this battery. So if I want to test, for example, a 100 milliohm impedance with a test current of only 100 milliampere, the result voltage or the voltage drop I will get is 10 millivolt. So it really can get swamped with noise easily and affect this measurement. But if I test with 10 milli or 10 ampere instead of the 100 milliampere, the voltage drop will be 1 volt, which is 100 times higher. It will be more susceptible to noise, and I will get a better resolution and accuracy in doing this measurement. Also watch the test current. If you are testing strobe resistance or the connections, usually these connections are in micro ohms, so it's not really a good way to doing it using a normal ohm meter or the ohm meter in your multimeter. It's better to use a micro ohm meter or DLR, or what we call digital low resistance ohm meter, because these test devices use a higher test current, which will give you a better resolution for the voltage drop and thus a better accuracy. Another thing, when you are doing this strobe test, it's really recommended to take a bidirectional DC resistance measurement. Don't measure it only from one side, swap the leads and do from the other side. The reason for that is because there is always going to be some DC current going through the batteries. So when you're doing it in both direction and taking the average, you will get a better reading and measurement. Instead, some of the test equipment, digital low resistance, have already this function built in them, and it will directly give you the average for the bi-directional, thus avoiding you the issue of the already existence current in the cells going through the string. Another pitfall, if you are doing strobe resistance measurement, whenever you are using a duplex leads, these leads which have the voltage and the current probe at the attached to other or near each other, one will inject current and the other will measure voltage. Whenever I'm doing this, it's going to be a relative measurement, not absolute one, because I don't have a uniform current density going through the strobe. It takes time for this current to be really distributed to give you a very stable reading. So when I'm doing this with a different probes, having different mechanical or different physical shape other from the previous one, I might have a different reading. So on this, I indicate that maybe there is a problem in there. But if you want to really overcome this issue, you can inject current through the whole string and then take the measurement on each strobe. This will neglect the effect of this current distribution for you. So when I'm using duplex probes to take this reading, I always put a 20% or compare it to the 20% tolerance from the previous reading because of this arrangement of the probes. Another issue, if there are some tiles which have a stainless steel hardware in the battery post for them, this stainless steel hardware is really can create some major challenges when you are testing this battery internal impedance, as this stainless steel hardware could have a high impedance and thus indicating there is a high impedance in the battery. So the best way really to do this test is to inject through the whole string of the battery and then take the measurement from each battery, and thus indicating only the voltage drop on the internal cell, not voltage drop on the stainless steel hardware. Another issue or pitfall some people might fall in is once I have, for example, a series string, there will be no issue in doing this measurement, but because the current will go only through one cell that I am measuring. But what happens when I have a parallel string I'm doing measurement to? The current will escape through the parallel path, and the tester will not be actually to see only the current going through my cell. It will see the total current, the escaping one and the one going through my cell. So the problem is that I'm not going to get any good reading of the batteries. This is why IEEE recommends segmenting the strings once I do this test to or ohmic test, so I can get a true readings. Because if I have one battery that goes bad, it's going to really change the reading for every battery I'm doing a test on the same string and the parallel one. And this will change current going through them, so I will never be able to isolate the battery without segmenting the string really. In this case, what you can do, instead of segmenting the string, you can use an extra CT. This CT will put on the parallel string, and it will measure the escape current going through that parallel string. And once this tester already knows the total current and also measure the escape current through the extra CT, it can subtract this extra current and give you the true reading for each cell that you are doing. This really make it easier for you when you have parallel strings by adding this additional extra measurement CT. Lastly, I will talk briefly on some maintenance schedules and see some of the recommendation, starting with the VLA, the flooded type cells. This presentation and webinar recording will be available to you, so I'm not going in depth about this recommendation. This is just an example for the vented lead acid or flooded types. We have recommended and minimum test done. The minimum is based on the US NERC as an example for you to see and check that for you, while the recommended is based on IEEE recommendation. Basically, if you want more reliability, you will do want to do more. You want to go toward the recommended rather than going toward the minimum test. But please don't go lower than the minimum for your batteries. So my advice to you is don't determine or determine what your resources availability for you, and come up with a base plan based on your resources and how critical your battery system is really are, and find something in between these two, recommended and minimum recommendations. We will basically see that both the minimum and recommended tests are basically the same, mostly basically the same, just that the time frame is slightly different between two. The recommended having more insensitive and a shorter time frame for the periodic tests. This is example for the flooded types. I have another example for the sealed type. Keep this slide for a few seconds if anyone wants to see it, and also for the nickel cadmium type. And with that, our presentation segment is concluded, so we are opening the floor for questions. I am sorry about the short delay happening in the beginning, and we take slightly more time of your table. We'll take few questions.
Okay, guys, so that's the end of the presentation. So if you have any questions, please write it now in the chat box. We'll give you, because at the moment we don't have any questions, so we'll give you at least 1 minute or 2 minutes to type in your questions if you have. And please be reminded that when you close this webinar, there will be a pop-up screen, and uh, a survey form will be displayed. So please fill that form, because that will really help us a lot in improving our future webinars. Okay, so we have a question here. Uh, how to detect a ground fault on battery bank? Okay, sir. This is another product. We have a what we call the battery ground fault detector or tester. So there will be another webinar for this one. Please uh, stay tuned, and you will see it how to detect this ground fault in the battery bank. But yeah, basically we can do it with our tester. We inject a AC current, and so we trace it using a clamp. So yeah, just to give you an idea on how to detect the battery ground. So any other questions, guys? We have a question here from Nito. How to know reference impedance value? Should we refer to data form? Well, when I ask these questions, Nito, from Andy, normally the factory gave you a data which has an indication of resistance only, but actually when they measured that resistance, it is actually they're measuring the impedance, as he said. So for the reference impedance, for example, we are going to do the byte or the battery impedance tester that we have. Uh, our software has an automatically identify the baseline if you don't have the historical data or the previous test result. And by that, you can assess the impedance or the difference between cells, the difference of the impedance between cells. Yep. So normally, if you don't have historical data, then our software has these features that will give you automatically the baseline, so that you can use it to compare per cell. Okay. So any other questions, guys? Since we don't have any more questions, um, at this point in time, I would like to say thank you everyone for joining us today, and hope to see you again next time. We still have a lot of webinars to come. Again, thank you so much. Thank you, Sumedi, and thank you, Grace. Have a good day.
Thank
Please
you,
stay safe.
Michael. Thank you,
Thank you,
Samedi.
Michael. Grace. Bye bye.
Bye bye, everyone.